So, Sakina, this is like a crash course. So we will try to finish your entire syllabus in 1.5 months. We just have few days of December, the whole January, and 2-3 days of February we will need. So for physics, there are two teachers who will be taking your syllabus. One is Amna. You must have attended one of the class of Amna. Na?
Yes, sir. Yes, sir.
So she will be taking your electromagnetism part, the entire first book of class 12, huh? Right, starting from electrostat to the electromagnetic wave. And I for
Yes, sir.
the
She told.
yeah, and I'll be teaching the second book, but the issue is I'm running this batch for quite a few weeks. So we have already finished ray optics and wave optics in this batch. Two chapters we have finished, chapter number 9 and chapter number 10. And we are going to start modern physics. So chapter 11, 12, 13, 14, all are left. So what we will do, we'll do first the whole entire modern physics, right? Starting from chapter number 11 to chapter number 14. Then I'll give you recordings of wave optics and ray optics, and you can discuss doubts with me. This is how we'll try to finish your second.
Okay, sir.
And just tell me very frankly, how is your physics? Like, how are your calculations?
Sir, my theory is good. Derivations are good, but like numericals are not that good.
Okay, good. Then you can do one more thing. We'll be starting a numerical solving workshop also, so you can join that workshop. So that workshop will help you a lot in numerical solving
Okay,
also.
sir.
So let's start with the classes and then we'll share you the timings of the workshop also. And you just want to do CBSE or you want to prepare for JE or NEET as well? Because that
No, sir. Only CBSE.
only CBSE right now. Fine, Sakina. So let's start the class. Let me admit others. Okay, so I didn't take last class. Atik sir have finished Prism, I believe. So what was the last topic that Atik sir did in Prism? Can anyone tell me the last topic that he did in Prism?
So minimum deviation of prism and prism formula.
Okay, that was the last topic that you did with it. Fine. So you did dispersion or not?
No, sir.
Dispersion you did too. Okay. So I'm starting modern physics from now. Uh, in the last 30 minutes of the class, we'll do some topics which are very, I'm doubtful about those topics, whether they are in syllabus or not, but we will finish it just to be on the safer side. So there are a few topics in the ray optics which were deleted. Then the guidelines came, no, these topics are being added. So there's not much clarity on those topics, but to be on safe side, we'll finish those topics. So in the last 20 minutes of the class, after 10 o'clock, we'll do those topics. But now I'm starting modern physics. So the topics that are left now, like modern physics and this thing, electronics, just give me 1 second. Yes. So the topics which are left now, that like chapter number 11, which is photoelectric effect. So chapter number 11 is photoelectric effect. Then after photoelectric effect, we have there's one more chapter which is atom. Then we have nuclear, and then we have semiconductor. So each chapter should not take more than 1.5 hours. Even nucleus we'll finish nucleus in 1 hour only. So all chapters will need one class to finish. And those all chapters, like right starting from chapter number 11, 12, 13, these are included in modern physics. And modern physics is the most scoring part of the syllabus. So before starting any particular chapter of modern physics, let's first discuss some general things about modern physics. Also on the group, I have shared these notes of modern physics. Huh? These are very old notes, but these have each and everything that you need for modern physics. So modern physics start with the concept of Einstein's mass energy equal. So in mechanics, we study conservation of energy, that energy can neither be created nor destroyed. If you can remember the syllabus of class 11, then in fluid dynamics, the whole of fluid dynamics was based on conservation of mass, that mass can neither be created nor destroyed. But when you do modern physics, when you come to the scale of nucleus or when you come to the scale of atom, then energy is not conserved. Mass is not conserved. Energy can be converted into mass. Mass can be converted into energy. So there is one relation which is known as Einstein's mass energy equivalence, E is equal to mc square. This E is equal to mc square relates energy and mass. This says if you have m mass and somehow if that mass get destroyed, then you get E amount of energy. And you can relate E and m as E is equal to mc square, where c is speed of light. How much is speed of light? Yes. How much is the speed of light? C. So the
Three
value of speed
meter
of
per
light,
second.
3 lakh kilometer per second. Huh? That is the value of speed of light, 3 lakh kilometer per second. So C is 3 into 10 raised power 8 meter per second. This is 10 raised power 8 meter per second. So you should remember all these values in SI. Huh? Next, we have Planck's quantum theory. And just one more thing. See, light, if you things which are around yourself, you can divide those things into two categories. The things around you could be a particle or it could be a wave. If I take this pen, then this pen is a particle. But if we talk about sound, sound is a wave. There are many differences between particle and wave. Can you give me one difference between particle and wave? Just one difference that you can think about between particle and wave. It's an
So can
open
you repeat
question
the
to.
question?
Yes. Can you tell me one difference between particle and wave? It's an open question to all. Can you tell me just one difference between wave and particle? No. See, the one difference is waves, particles have mass, but usually waves are massless. They don't have mass. The second difference is particle is localized. Yeah, it means you can tell the exact position of a particle. In this room, I can tell the position of this pen. This pen is a particle which is localized. But on the other hand, waves are delocalized. I can tell the exact position of wave in this room. Waves are pretty delocalized. So particle is localized, but waves are delocalized. That's one difference. Light is a particle or a wave?
Wave.
Sushma,
Wave.
light shows both the characteristics. Light behaves both like a particle as well as a wave. So in the first chapter of photoelectric effect, we will consider light as a particle. We will study the particle characteristics of light. So when we start the particle characteristics of light, the first topic that comes is Planck's quantum theory. So Planck's quantum theory says the light is not a continuous wave. Light consists of photons. Just give me 1 minute. I'm changing the slides. Yeah, these are my slides. Yeah. So the Planck's quantum theory says that light is not continuous. It's not a continuous wave. It consists of particles, and each particle is a packet of energy. Earlier, they call this as quanta. Now we call these particles as photon. These are the particles of light. It's quanta or photon. So according to Planck's quantum theory, light is not a continuous radiation. It consists of particles, and those particles are photons. These particles are moving at a very, very high speed, which is the speed of light. It's moving with a very, very high speed, which is speed of light. Due to this high speed, they appears as continuous. But actually the light coming from the bulb is not continuous. This have packets, and those packets are traveling with a very, very high speed, which is the speed of light.
Sir, is there is any space between two continuous photon like packets a minute?
That traveling with a very high speed, you can't measure the space between them. But yes, there is a time interval between one photon and another photon. There's a time interval. Now, according to Planck's quantum theory, the energy of photon is h nu, where nu is the frequency. Energy depends upon the frequency of photon. And I believe you remember this relation. We have used this relation in wave optics also. The speed of light is frequency into wavelengths. You can say that
Yes.
frequency is speed by wavelength. So instead of this frequency, I'm using c by lambda. So this is the expression of energy at c by lambda. Energy of a photon is at c by lambda, where h is Planck constant, and Planck constant is 6.626 into 10 raised power minus 34 joule seconds. See, in this chapter, there are many definitions. So the notes that I have shared with you are very detailed notes. They consist of all definitions. So right now we'll concentrate on the concept only. So I'm not writing definitions here. I've already shared the notes, and those notes have all definitions. I will not write definition for this chapter. So Planck's quantum theory simply says that light consists of particles, which are known as photons. The energy of photon is h nu or hc by lambda, where nu is the frequency of light and lambda is the wavelength. Nu is frequency, and this lambda here is the wavelength of light. This is wavelength. This is the This is the value of Planck constant, 6.626 into 10 raised per minus 34 joule seconds. Now, there is one small issue with the formula. The issue is the calculations. Calculations are very lengthy. In modern physics, we don't use joules as a unit of energy. Joule is a very big unit. When we usually talk about atoms or electrons, joule is a very big unit. We need smaller unit of energy, which is electron volt. 1 electron volt is 1.6 into 10 raised power minus 19 joule. So in modern physics, usually we keep energy in electron volt. We avoid joule because joule is a very big unit. If you want to use joule in modern physics, it's like you draw a line on your notebook and you want to measure that line in kilometer. Kilometer is not the appropriate unit to measure that line. That line should be measured in centimeters. Just like that line, if you want to measure your energy of an atom in joule, then joule is a very big unit. You will get your energies in terms of 10 raised to the power minus 13, minus 15. So the convenient unit here is electron. Now, when we use electron volt, there is a big issue. See, when we use this formula, E is h nu or hc by lambda, the value of h is this 6.626 into 10 raised to minus 34. So, Hishma, what is the unit of Planck constant here in this relation? This value of Planck constant is in SI unit or in non-SI unit? Hishma. The value of Planck constant here, is it in SI unit or non-SI unit? Shaifullah.
Non-SI.
Non-SI. Joule is non-SI unit.
SI.
SI, na? The SI unit of energy is joule. So this value of Planck constant, which is 6.626 into 10 raised power minus 34, this is the SI unit. This is the value of Planck constant in SI system. But if you want to convert this energy into electron volt, then calculation would be very lengthy. A shortcut method is, if you want to keep your calculations short, E is hc by lambda. Instead of hc, you can use 12400. This lambda, instead of converting this lambda into meter, you can keep this lambda into angstrom. So if you keep your lambda in angstrom and you divide this by 12400, then you will directly get your energy in electron volt. Say I'm giving you an example why this expression is very helpful. Let's say the wavelength of light here is 4000 angstrom. This is the wavelength of light, which is 4000 angstrom. I asked you to calculate energy for this particular wavelength. What is the formula of energy for calculating this wavelength? Akshay? I want to calculate energy for wavelength of 4000 angstrom. What's the formula for calculating energy of light in
Planck's
theta?
constant into frequency.
I don't have frequency, I have wavelength. So what expression should I
C
use?
lambda.
Yes.
Hc
Hc
by
by
lambda.
lambda.
So energy will be Hc by lambda. The value of H is 6.626 into 10 raised to the power minus 34. I'm just giving you an idea how lengthy the calculations could be if you use this relation. C is the speed of light, which is 3 into 10 raised to the power 8. Then your lambda is in angstrom. You have to convert this lambda into meters. So that's 4000 into 10 raised to the power minus 10. Sakina, what should be the unit of this energy? This will be joule or it would be electron volt?
Joule.
Joule. Because we are using all quantities in SI units. So energy should also be in SI unit, use in joule. But you need energy in electron volt. So to convert this energy in electron volt, what you will do is you will divide it by 1.6 into 10 raised to the power 90 minus 90. You will divide it by this term, 1.6 into 10 raised to the power minus 90. Then this will convert into electron. This is the first method to calculate your energy in electron volt. The second method is you can directly use this relation, or you can use this relation 12400 by lambda and angstrom. So this will be 12400 by lambda and angstrom, which is 4000 angstrom. So this 20 will cancel this 20, 4 3s are 12, 1. So this will be 3.1 electron. So if you use this relation, this will save your time. So instead of using 12400 by lambda, this Hc by lambda, try to use this expression 12400 by lambda. You will get your energy in electron.
So they will give wavelength always in angstrom or
Yeah. Energy wavelength for this relation will always be in angstrom. But if you are using this relation Hc by lambda, then your wavelength should be in meter. You can use all SI units.
so in question they give it in meter or they give it in angstrom, the
They
wavelength.
usually give you in angstrom. In question, they will give you in angstrom. Usually in angstrom. This is Einstein's mass energy equivalence. The next is rest mass of photon is 0. So if you have photons which are at rest, so their rest mass would be 0. But when photons move, they gain some mass. See, up to the first book, the classical physics, we have studied that mass does not varies with speed. Mass remains invariant with speed. But actually, mass increases with speed. This is famous Einstein's postulate of relativity, that m is m naught by root over 1 minus v square by c square, where m naught is the rest mass and m is the moving mass. Means if an object is at rest, its mass is something else. When this object starts moving, its mass will increase. Mass increases with the motion. If you keep on increasing the velocity of body, its mass will keep on increasing. We don't observe it in the day-to-day life because the speed which we deal with are very small as compared to the speed of light. But here in modern physics, your particles will travel to the very, very high speeds. So their mass will vary. So from now onwards, we will have two types of masses. One is the rest mass, means the mass of the body when body is at rest. Another is the moving mass, means mass of the body when it is in motion. And this is the relation. Next is the rest mass of photon is 0. If you have photons and you say that these photons are at rest, then its rest mass will be 0. But you can calculate the mass of photons when they are in motion. So to calculate mass of photons when they are in motion, we can use two equations. If I consider that m is the moving mass of photon, then I can calculate energy of photon as mc square. Where if I say that m is the mass of photon at speed c, I can write the energy as mc square. Is there any other formula to calculate the energy of photon, Yashika? Yashika, is there any other formula to calculate the energy of photon?
Sir, h times frequency.
H times frequency. So the energy of photon you can calculate from two methods. You can write this as mc square, or you can write h times frequency. So from here, you can write that mass of photon is h nu by c square. So this is the mass of photon when they are moving at a speed v(c). The rest mass is always zero. If you have photons and he asks you the rest mass of photon, that's zero. This is the mass when photons are moving with a speed c. So from here, you can conclude that mass of photon is directly proportional to frequency. So if you increase the frequency of light, then mass of photon will increase. So I have a question, like I have two photons. One is of red color. One photon is of red color. Then I have another photon and this photon is of blue color. Noah, can you compare the masses of these two photons? Which is the heavier one? The photon of red color and photon of blue color. Which one is the heavier photon?
So the red one.
Why?
Because the frequency of the red color is higher than that of blue, I guess.
Okay. Akshay, which one is the heavier photon? Red or blue?
The red ones.
The red one. Nabil?
The blue, sir.
No, so the blue one. It is
Blue one. See that
coming in
the
denominator.
wavelength of red color is greater than the wavelength of blue color, not the frequency. Frequency and wavelength are inversely proportional. It's the wavelength which is greater. But frequency of red color is less than the frequency of blue color. Frequency and wavelengths are inversely proportional. So mass of photon of red color is less than the mass of photon of blue color. These are small conceptual questions that one can ask. Is it clear up to here?
Yes, sir.
Okay, just note down. So this is just a classification that I gave. I gave this introduction in the starting of wave optics also. That when we consider light as a wave, we study interference and diffraction that we have already done in wave optics. But when we consider light as a particle, then we study photoelectric effect. So the chapter photoelectric effect will consider light, the particle characteristics of light. Just note it down fast. Can I scroll it if you have written?
1 minute, sir.
Please tell me once you have written it. Can I scroll now?
1 minute, sir. Done, sir. Sir, do we need to learn that equation as well? That m is equal to m0 by under root 1 minus v by c square.
It's not a part of syllabus, but really good if you know this equation. This equation is not a part of syllabus.
Yes, sir.
Write down these relations also. So now you know that you have to use this relation. Huh? This will save time. Can I scroll it now?
1 minute, sir. Done, sir.
Please write this example also. This could be a 1-marker question. Just have to compare the masses of photons of different colors. Okay. After this, there are two terms which one should know before starting the photoelectric effect. One is energy of photon and another is the intensity of photon. The energy of photon depends upon frequency, and frequency means color. Like the color of light depends upon frequency. So energy depends upon frequency. If I say I'm changing frequency, that I'm changing color. So the energy depends upon frequency. Energy is independent of number of photons. It does not matter you have one photon of red color or you have 1 lakh photon of red color. If you have photon of red color, then they will have same energy. It's independent of power of bulb. It does not matter whether red light is coming from a bulb of 100 watt or red light is coming from a bulb of 1000 watt. If it is red, that means frequency is same, energy will be same. So this is one thing which is different from the wave optics. In wave optics, the power of bulb will decide the energy of wave. But in particle nature, when you consider light as a particle, that light have photons, then energy will depend upon frequency. It will not depend upon number of photons. It will not depend upon the power of bulb. The next is intensity. So when we say intensity, then intensity means number of photons per unit area per unit time. So intensity is related to number of photons now. It depends upon the power of the source. Means if you have a bulb of 100 watt, they are emitting less number of photons. But if you have a bulb of 1000 watt, they will emit comparative larger number of photons. So the wattage of bulb, the power of bulb controls the number of photons, which depends upon intensity. And see, this is absolutely independent of frequency. It's absolutely independent of frequency. Intensity does not depend upon frequency. So this thing which should be very, very clear in your mind. When we talk about energy of photons, that means energy depends upon frequency. We are talking about the frequency of radiation. When we talk about the intensity, we are talking about the number of photons, which does not depend upon frequency, which depends upon the intensity, which is basically the power of the bulb. So I wrote this example also here just for the clarification that if intensity of light from 1000 bulb is more than 100 watt bulb. So is it clear? These two things, energy and intensity, because photoelectric effect is a very small chapter, a very small topic. There's one concept only, that is photoelectric effect, but you have many, many graphs to draw. To draw graph, to handle conceptual questions, the difference in energy and intensity should be very clear. You will see as we proceed that almost in every topic he will draw graph, and in graph he will either use frequency or intensity. So right from the beginning of the chapter, the difference between energy and intensity should be clear. When we say energy of photon, we are talking about the frequency. When we say intensity of photon, we are talking about the number of photons, which depends upon the power of it. We can use one more unit of energy, 1 mega electron volt, which is 10 raised power 6 volt. This we have already discussed. The next definition is the work function. No need to write definitions. The notes that I am sharing with you have all definitions in very detail. No need to write definitions. Just write the fact that we will be using in numericals. So that's okay. Just note it down. Then we'll start the work function. Just note down this energy and intensity. And remember, this definition of energy and intensity is for particle nature of light, particle picture of light. If you look at the wave picture, then energy will depend upon intensity. In electromagnetic waves, we did that intensity is energy per unit area per unit time. So that's a huge difference between the wave picture and the particle picture of light. Sakina Bas, are you getting it?
Yes, sir.
Yes, sir.
This is very, very scoring topics. Photoelectric effect, atom, nuclei, and this thing, semiconductors. Very, very scoring topic. Miraj, clear? Alia, doubts? अरे फिजिक्स में मार्क्स कितने हैं प्री बोर्ड? कितने का अटेम्प्ट किया था? Okay.
Yes, sir, done.
Yeah, I need 4 more lectures to finish the syllabus. After these 4 lectures, I will start the numerical solving workshop. We'll be doing just numericals. That will help you in MCQ. You all vacation winter break have started?
Yes.
Nabil, Ishma,
Yes, sir.
Rashi.
Yes.
Okay, so we can take some extra classes. I need 5 classes, huh? So I just want, and these are very simple topics. So maybe I will take those 5 classes in this week only, and we'll finish the syllabus by the end of this. Because in January, I want to do some numerical solving workshops. Okay, okay, no.
So should we write this question?
No need to write this question. That's it. So you have written up to here, no? Okay. Then just write this one, this thing. 1 mega electron volt is 10 raised power 6 electron volt. Just write this. 1 mega electron volt is 10 raised power 6. You should know this thing. Mega means 10 raised power 6. So 1 mega electron volt is 10 raised power 6 electron. Okay, now this was the introduction of modern physics, huh? General modern physics. Now we are coming towards the exact photoelectric effect. So to understand photoelectric effect, let's first start with the work function. What does work function mean? See, if you have an atom, this is an atom. Yes, Akshay. More? See, what does work function means? Work function means if you have a metal surface, and these are the topmost electrons of the metal surface. These electrons are bounded with their atom, with their respective atoms. If you want to eject these electrons from the metal surface, the minimum energy required is the work function. So what is work function? Minimum energy required to eject electrons from metal surface. And cesium is the one which have minimum value of work function. We will represent work function by phi. So no, we don't read it now in the new place. So this is work function, minimum energy required to eject electrons from the metal surface. After work function, let's start with the photoelectric effect. What does photoelectric effect? See, this is one example. This example consists of almost everything about photoelectric effect. If you can understand this example, then that means photoelectric effect is over. We just have to repeat these things with graph and with equation. The whole concept of photoelectric effect is in this example only. See what this example says. This example says you have an electron. The work function of the electron is 2 electron volt. And you incident a photon of energy 1 electron volt. Will there be a photoelectric effect here? Miraj. The work function is 2 electron volt and you incident a photon of 1 electron volt. Will there be photoelectric effect here? Miraj, you're not audible. Because the energy of incident radiation is less than work function, so there is no photoelectric emission. Then you incident a photon of energy 2 electron volt. Work function is also 2 electron volt. Energy is equal to work function. So the photon has sufficient energy to eject electron. So yes, PEE means photoelectric emission. Photoelectric emission will take place now. But you get you provide energy just equal to work function. So electrons will not have any kinetic energy. The kinetic energy of electron will be zero. So electrons will not move. They will eject from the metal surface and will come to rest. But now, if you incident a photon of 3 electrons, work function is 2 electron volt. Energy is greater than work function. So obviously system will undergo photoelectric emission. And the extra C, the energy required to eject electron is 2 electron volt. You're providing 3 electron volts. So this extra 1 electron volt will go into the kinetic energy of electron. So electron will have a kinetic energy 1 electron. So instead of 3, if I incident a photon of 4 electron volt. Now this, how many electrons can this photon eject, Miraj? The work function is 2 electron volt and photon have energy of 4 electron volt. How many electrons can this photon eject? Minashi,
Sure, one.
why 1? 2. That's a common misconception. 1 was the right answer. 2 is a very common misconception. See, if you look at this diagram, they will always say it will eject 2 electrons because for 1 electron, the energy required is 2 electron volt. Now we are providing 4 electron volt. So ideally, this photon should eject 2 electron volt. But see, in photoelectric effect, this is the collision of electrons and photons. Photons are behaving like charged particles, like particles. So when these photons comes and collide with electrons, this is collision of electrons and photons. So for this collision, the energy of photons should be equal to or greater than the work function. Here, this photon can collide only with one electron. The cross section or the size of electron and photon is such that one photon can collide with one electron only. One photon cannot collide with 2 electrons. So although this photon have energy which is sufficient to eject 2 electrons, but it cannot collide simultaneously with 2 electrons. It can collide with 1 electron. So it will collide with 1 electron and will eject the electron. The extra energy will go to the kinetic energy. So remember, it's a 1 electron and 1 photon phenomena. 1 photon will collide with 1 electron. 1 photon cannot collide with 2 electrons. Or 2 photons cannot collide with 1 electron. If I give you this example, you have 2 photons of 1.5 electron and 1.5 electron. Can this single photon eject this electron? No. The energy of one single photon is 1.5 electron volt. Can this single photon eject this electron? Akshay? Can this single photon of 1.5 electron volt, can it eject this electron?
No,
Why not?
because
Because its energy is less than the work function, right? But if you have 2 photons, then collectively their energy is 3 electron volt. It seems like now, yes, now they should eject this electron. Because if you take the collective energy of two photons, 1.5 and 1.5, it becomes 3 electron volt. So 3 electron volt photons can eject 1 electron volt whose work function is 2 electron volt. But again, the problem is two photons cannot simultaneously collide with an electron. It's a one electron, one photon phenomena. At one time, only one photon will collide with one electron. That's again a problem. Two photons cannot collide with a single electron. It will never happen. So no photoelectric emission. So you should remember this thing. One photon will collide with one electron. If you want to increase the kinetic energy of electron, then you will increase the energy of photon. But if you want to increase the number of electrons, let's say I want to eject 100 electrons, then what should I do? Nabil, should I increase the frequency of photon or the number of photons?
It's number of photons.
Number of photons. And number of photons, Nazia, depends upon energy or intensity?
Intensity.
Intensity. So if you want to increase the number of emitted electrons, then you have to increase the intensity of radiation. If you want to increase the kinetic energy of electrons, then you have to increase the frequency of photons. Do it. So there's no need to write the definition of work function. That's already in your notes. But draw this diagram. Do this example. If you have any issue, I can discuss it again. So this is something very, very, very important. So there are three important things that you can learn from this example. One is for photoelectric emission, energy of photon should be equal to or greater than the work function. Second, if you want to increase the kinetic energy of electrons, then you should increase the energy of photon. And if you want to increase the number of electrons, then you should increase the number of photons. Do it fast. Written? Can I scroll it? Sakina, Akshay, Arpit?
Yes, sir.
Yes.
Sure. Okay. The next is Hertz experiment.
Sir, 1 minute, sir.
Yes.
Yes, sir. Done.
Okay. So next is Hertz experiment. To study this photoelectric effect, Hertz did a very basic experiment. What he did is he took this evacuated tube. Evacuated tube means this tube have vacuum. There's no medium inside the tube. This is one plate. He connected this plate with the cell, another plate with the cell also. So There is no connection between. And he connected the emitter here. So will there's nothing, see, there's no photons here also, nothing. So what do you think? Will there be any current in the circuit? Yes. Will there be any current in the circuit? Yes or no? This is your evacuated tube. This is one plate. This is connected to the negative terminal of the battery. This is another plate which is connected to the positive terminal of the battery. And this is the emitter. I'm just asking, will there be any current in this circuit right now? Or no? Yes or no? Ishma, Ishma, will there be current or not?
There won't be.
Why? Why there won't be any current in the circuit? It's an open circuit, right? The current will flow when you have a closed circuit. So there is no connection between the two plates. So it's simply an open circuit. So in an open circuit, current will not flow. It's an open circuit one. So there won't be any current. But next, what you can do is you can take an opening here. Then Hertz, what he did, he opened this thing, make it transparent so that light can enter into it, and he incident some photons on the plate. And the energy of photons that he took is greater than the work function. Then what happens here is electrons will eject, and these electrons will move towards the positive end of the plate. So when electrons travels from one plate to another, then currents start flowing in the system, and you will have some reading in the emitter. So the emitter will show some reading, milliampere. So the cause of the reading is not this cell. The cause of the reading is the emitted photoelectrons. So this milliammeter is measuring the photocurrent. It's simply measuring the photocurrent. It's not measuring anything else. It's measuring the photocurrent. Now, we can draw some conclusions from here. Like current depends upon the number of electrons, and the number of ejected electrons depends upon the number of photons that were incident. And the number of photons means intensity. So we can conclude that photoelectric current, we can conclude here that photoelectric current will depends on number of electrons, that is on number of incident photons, that is on intensity. Which means if you increase the intensity of radiation, that means you are increasing the number of photons, due to which the number of ejected electrons will increase. So photoelectric current depends upon intensity. It's independent of frequency. Does not matter with what kinetic energy the electrons are traveling. Because if you keep on increasing the energy of photons, the number of electrons are not increasing, just the kinetic energy of electrons are increasing. So current will not increase. Current will increase only if you can increase the number of electrons. So photoelectric current depends upon intensities, does not depends upon frequency. So if you plot some graph like current versus intensity graph, you can see this is an experimental graph. This is current and this is intensity. Current increases with intensity. Minashi, if I draw the similar graph for current versus frequency, what should be the shape of the graph? Minashi, on the x-axis, instead of intensity, if I take frequency, then what should be the nature of the graph? Akshay, yes, Minashi will tell you.
Same.
Same graph. Okay. Akshay,
So can you repeat the question?
sorry, I'm asking if I draw the same graph, current versus frequency graph. Instead of intensity, if I take frequency, what should be the nature of the graph? Yes, Akshay.
Like it will be like
Okay, just tell.
parallel to
Yeah, Minashi, just tell me one thing. Current depends upon frequency or current is independent of frequency? Minashi, the photoelectric current depends upon frequency or it's independent of frequency?
Independent of frequency.
So if it is independent of frequency, then on changing frequency, current should not change, right? So can
Yes.
you guess the shape of the graph now?
Mm. The
Yes.
opposite of this.
No, no. Yashika, can you
Sir,
guess the shape of the graph now?
Sir, flat
Straight
line.
line.
Straight line, parallel to the intensity axis, this axis, frequency axis. You keep on changing the frequency, current will not change. Current is independent of frequency. So this will be the shape of the graph. So these two graphs are important. If you look at previous year's questions, these are being asked. So in photoelectric effect, there are two types of questions, one on graph, which carries a major weightage, and then you have few numericals. There are not many numericals in photoelectric effect, there are few numericals. Note it down, please. And tell me if you still have any doubt in it. Noha is still going to school nowadays.
Yes.
Pre-boards or regular classes?
So pre-board.
Can you share your timetable with me, like the pre-board schedule?
Okay, sir.
I will see if I can plan 1, 2 extra classes in between them. These are the type of chapters that we can do in a single sitting also. Not these topics does not have many type of numericals. They can be done in a single sitting also.
Sir, can you scroll up? Done.
Can you please share the marks of your recent pre-board exam of physics? Because I believe your school must be taking multiple pre-boards now. See, basically, I'm planning two types of classes. So one is just based on CBSE and another for the JE point of view. So it will help me to decide which batch would be better for which. So please share the marks of your pre-board exams. I should at least have an idea now how you people are performing. I'm waiting for the marks. The marks of the recent pre-board exams. Okay, okay, sir. Yashika, Arpit, Noha, Saifullah, Minashi, Nabil. Okay. Okay. Okay, Shikar. Okay, okay, no. No need to write this thing. I'm just, this is what we have discussed. Can I scroll it? Can I scroll it now?
Yes, sir.
So, okay, then there is one thing which is stopping potential or cutoff potential. To understand what the stopping potential or cutoff potential means, let's study this rough data that I have taken there. What does this data mean? This is the plate. This is the plate. Let's say this plate is positively charged. Huh? So what does this positively charged plate do with the electrons? It will attract electrons. So right now I'm considering about the potential of this plate. Basically what we want to do is we want to see how this potential can affect this current. We just want to see the effect of potential on this current. To see the effect, I take some rough data. What I take is, I said from this plate, 100 electrons gets emitted. The potential of the plate is positive, like plus zero potential. And some 10 electrons reach the second plate. Means the 90% of the electrons gets lost. How the electrons losses? See, when electrons eject from the plate, then there are chances that these electrons will deviate from their path and they will collide with the walls of the tube. So when electrons collide with the walls of the tube, they lose energy. Electrons can collide with one another also. So when they collide with one another, they lose energy. So these electrons will keep on colliding with the walls of the container. And after each collision, they will lose energy. So out of the 100 electrons which were ejected from this plate due to photoelectric emission, only 10 electrons reach here. So the current in this emitter will be corresponding to these 10 electrons only. Now, if I increase the positive potential here, see the positive potential of the cell here, the positive potential of this plate will attract more electrons because positive will attract the negatively charged electrons. So more electrons will reach here. So if we increase the positive potential, more electrons are reaching here. We keep on increasing the positive potential, the number of electrons which are reaching this plate keep on increasing. Means the current in this emitter will keep on increasing. On increasing, we reach a point where the positive potential is 20 volt. All 100 electrons which were ejected reach the second plate. That means this is the maximum. This is the saturation. The current in this emitter is maximum now. So if you increase the positive potential further, see the 100 electrons, photons can eject only 100 electrons. So it does not matter how strong potential you give. The extreme that this potential can do is it can attract all electrons, attract all 100 electrons. So the current becomes saturated. Current is not increasing. Is it clear up to here? Minashi, Ishma, Arpit?
Sir, can you explain again?
Yes. See, this is the tube. This is the tube, okay? This is plate. And let's say we are providing positive potential. You incident some photons here. You incident 100 photons. So 100 electrons will get ejected. This is a variable battery. The potential of the battery is zero. You didn't provide any potential. So only 10 electrons reach here. 90% electrons are lost. The reason is when electrons are ejected from this plate, there are chances that these electrons will deviate from their path. They go here. One electron can go here and can collide with the walls of the container. So majority of electrons get lost. Very few electrons reach the second plate. Is it clear? Jasola, up to here?
Yes, sir.
So Safullah, what do you think? What will happen if I keep on increasing the positive potential? What this positive potential will do? It will attract electrons or it will repel electrons?
Sir, it will attract more electrons.
So it will, if it attracts more electron, that then what will happen with current? Current will remain constant or current will increase?
Current
Yes,
will
sir.
increase.
Current will increase. So see here, I'm increasing the positive potential. So as I increase the positive potential, the number of electrons reaching the second plate will increase. And finally, a time will come where all electrons which are ejected from this plate, this particular plate, will reach this plate. We call this as the saturation. The current is maximum now. Current cannot increase further. You keep on increasing the potential, the current will not increase. It's the saturation current. Is it clear?
Yes,
Akshay?
sir.
Yes, sir.
Akshay, what will happen if I make the potential of this plate as 100 volt plus 100 volt? What will happen? Current will increase further, it will remain constant. Akshay, if I make the
Will remain
potential of this
constant.
plate as 100 volt, what will happen with the current? It will increase or it will remain constant?
Will remain constant.
Why? Why it will remain constant? Akshay? Nabil, why the current will remain constant?
Because already at plus 20 volts, all the electrons are being attracted. And
Because
beyond that,
yeah,
beyond that,
because
it is further no change.
right, because all electrons are already reaching here. Na? If you keep on increasing the potential, then potential cannot create new electrons. So current will saturate. Hishma, instead of positive potential, if I give negative potential to this plate, then what will happen? Instead of positive, I take the negative potential. Now, this will attract electrons, it will repel them.
It will repel.
It will repel. So, Nazia, what do you think? When we provide 0 volt, then the electrons reaching the plate were 10. If I provide minus volt, then the number of electrons will be 10, less than 10, or it could be more than 10. Nazia.
Uh,
Should I repeat the question?
yes, sir.
I'm asking when we provide 0 volt, then the electrons which were reaching the other plate were 10. Now, instead of positive potential, I'm providing negative potential here. I'm giving negative potential to the plate. What will happen with the electrons? The number of electrons will be greater than 10, less than 10, or remain 10.
Less than 10
Why? Why less than 10?
because the electrons will be repelled by the negative terminal and no current will flow through the
Yes.
microampere.
Yes. Electrons will be repelled by the negative potential. Right, you're right. So without any potential, 10 electrons were reaching, but now if you have negative potential, this negative potential will try to repel electrons. So the number of electrons will decrease. Let's say you have 7. When you increase the negative potential more, the number of electrons reaching the plate will decrease further. And you keep on increasing the negative potential, one negative potential will come at which no electron will reach this plate. This negative potential is known as stopping potential, or we can call it as a cutoff. So stopping or cutoff potential is that negative potential corresponding to which your current will be zero. So what happened at stopping potential? At stopping potential, the potential repel all electrons. This can happen only if the kinetic energy of electrons is equal to repulsive energy of plates. This line, kinetic energy of electrons is equal to the repulsive energy of plate. Then only the current could be zero. Current zero, photoelectric current becomes zero. That means no electron is reaching the other plate. Electron cannot reach the other plate only if they are fully repelled by the negative potential. So you can say the kinetic energy of electron is equal to repulsive energy. And we represent stopping potential or cutoff potential by V naught. So we can write kinetic energy is EV naught. Energy you can write as charge multiplied by potential difference. This is how we can write expression for energy. Charge multiplied by potential difference, EV naught. That's kinetic energy. That's kinetic energy, EV naught. So kinetic energy of electrons is equal to repulsive energy at cutoff potential. And this is the relation from where you can calculate the stopping potential. Kinetic energy is EV naught. Is it clear, the concept of stopping potential or cutoff potential?
Yes, sir.
Okay. So, Sakina Abbas.
Yes, sir.
Yes,
So,
sir.
Sakina, what do you think? There are two Sakina. I'm talking to Sakina Abbas. Sakina Abbas, she have first class today. So, Sakina Abbas, what do you think? The kinetic energy, not the kinetic energy, the stopping potential depends upon the frequency of radiation or depends upon the intensity?
Sir,
Stopping potential depends upon the frequency of radiation or depends upon the intensity of radiation? That's what I'm asking.
frequency.
Frequency. Why? Why you said frequency?
Uh,
You are right. Your answer is correct. I'm just asking about the argument. Why you said that it depends upon frequency?
because of the charge of electron.
No, no. Sakina, second Sakina. Sakina, can you answer? Why? Why?
Can you repeat the question, sir?
The question is stopping potential depends upon frequency. This is the fact. Why? Why? Can you explain why stopping potential depends upon frequency of radiation? Why not on intensity? Okay.
Because the emission of photoelectrons will only take place when there is certain frequency is incident.
That's partially correct, but not the exact answer. Okay, let's see if anyone else can answer it. Saifullah, will you try? Why stopping potential depends upon frequency of radiation? Yashika. Arey? Nabil Ahmed.
So stopping potential depends upon the kinetic energy of the electron, and the kinetic energy of the electron depends upon the frequency of the photon.
Right. Yes. So this is what we have discussed now in the starting example, that kinetic energy depends upon the frequency, and stopping potential is related to frequency. That's why stopping potential should depends upon the frequency of radiation. And kinetic energy is independent of intensity. So stopping potential does not depends upon the intensity. It's independent of the intensity of radiation. It does not matter whether you are using a 100-watt bulb or a 1000-watt bulb. For both the bulbs, your stopping potential will be same. So, and there's one more interesting thing, that is saturation current. This saturation current. Okay, let's come to Hishma again. Hishma, this saturation current here, on which factor this saturation current depends? This depends upon the intensity or it should depends upon the frequency? Current, I'm asking.
It will depend upon intensity.
Intensity, yes. Current depends upon number of electrons, which depends upon number of photons, which is intensity. So saturation current depends upon intensity. So if I plot a graph, see on y-axis I'm taking current in milliampere. On x-axis I am taking potential. I'm varying my potential from minus V naught to some positive value. So let's keep potential 0 first. So potential is 0. You have some current, this current corresponding to these 10 electrons. So as I increase the positive potential, the number of electrons are increasing. That means current will increase, which is clear for this portion of the graph. See, as we increase the positive potential, current will increase and then it becomes saturated. Saturated means your bigger current becomes constant. If I increase the potential further, the current will not change. Now, if I take potential to be negative, stopping potential, then what happens? Current decreases, and at stopping potential, your current comes out to be 0. So this is the graph between current and the potential. Is it clear? This is a very, very important thing.
Yes, sir.
So, great. Note it down. Then we will discuss some questions, some conceptual questions on this concept. We will write from here.
But in this chapter, there are numericals.
Yeah, there's just one formula. On that formula, you have 3 numericals. That's it. We'll do it. Today we'll do it. No need to draw this thing. This data. I just take some random data to explain what is the stopping potential. No need to write this. Am I audible?
Sir, done.
My voice is clear now.
Yes, sir.
Can you scroll it now?
Yes, sir.
These two statements are very, very important for conceptual questions and graph. Stopping potential depends upon frequency. It does not depend upon intensity. And on what factor does saturation current depends, Alia? On what factor does saturation current depends? Yes, saturation current depends upon intensity. Saturation current does not depend upon frequency. It depends only over intensity. It's independent of frequency. Please tell me if you have written it. Can I scroll it, Akshay? Saifullah?
1 minute, sir.
This is very, very important graph for exams. If you go through the previous year's questions, you will see that this is a very, very common question. But this question comes with two variations. Tell me once you have written.
Can I scroll it now, Akshay? Saifullah?
Yes, sir.
Now, this question comes with two variations. See, he's asking you to plot potential versus current graph for radiations of different intensity and same frequency. So, Nazia, what does same frequency means? What does this word same intensity means? Same frequency means stopping potential will be same or it will be different? Nazia, when you plot
Yes, sir.
graph, you have to decide for different radiations, the stopping potential will be different or it will be same. The question says for radiations of different intensity and same frequency. So you have radiations which have same frequencies. For these radiations, stopping potential will be different or same.
Same, sir.
And what about the saturation current?
The current will vary.
Will vary. So you can think of a graph, the same type of graph for different radiations, for which stopping potential will be same, but intensity will be different. So saturation current will be different. So this will be the graph. Same stopping potential, different saturation currents for different intensities. Is it clear for everyone? Ishma, Akshay, Noah.
Yes.
Yes, sir.
Next, for the next question. Plot V versus I graph for radiations having same intensity but different frequency. Intensity is same, but frequency is changing. What does this mean? Same intensity means stopping potential is same or saturation current is same? Yes, common question. Saturation current is same. Frequency is different, that means stopping potential is different. So we'll have this type of graph. See, you have three frequencies, all have different the stopping potential, but for all the saturation current is. These are two important. Note it down. Then we will start the last part of this chapter, that is Einstein's equation. So you can get few numericals on Einstein's equation.
So the wave nature of matter part is in this chapter.
Yeah, that de Broglie happens. That's just one line. So collectively, now this chapter takes 3 or 4 classes. This whole topic, all three chapters, and something very very scary. So by the time you prepare the first chapter, electric charge and field, that much of time you can prepare all three chapters of modern physics. Okay, so everyone have written up to it. Huh? Okay, the last part of photoelectric effect, and that is the Einstein's photoelectric equation. So Einstein's photoelectric equation is a simple statement which simply says simple statement says if you have a metal plate, photoelectric plate, and this is an electron, the work function of the electron is phi naught. You incidence a photon on the electron, the energy of the photon is E, and the kinetic energy of emitted electrons is Ke. This is the kinetic energy of emitted electrons. E is energy of incident photons. Phi naught is the work function. Ke is the kinetic energy of emitted electrons. So Einstein's photoelectric equation simply says that kinetic energy is the energy of photon minus work function. This is the Einstein's photoelectric equation. Kinetic energy is energy of photon minus phi naught. This is something that we have discussed in the first example when we started photoelectric effect. Now, next, what you can do is you can convert this equation in various forms. So what now we will do, we will convert this equation in various forms. So what we can do is, if I say that nu is the frequency of incident radiation, then you can write this E as h nu. If you say that nu is the frequency of radiation, then your E will be h nu. So instead of E, you can write h nu. So it becomes h nu minus phi naught, the second equation. We can make one more change. Instead of frequency, we can convert this in terms of wave. We can just put the value of stopping potential here also. So let's first put this in terms of stopping potential. K is EV naught. So in this kinetic energy, I can substitute instead of kinetic energy EV naught. So if I substitute EV naught, its EV naught is h2 minus phi naught. So the first expression, kinetic energy, energy and work function, kinetic energy, frequency and work function, stopping potential, frequency and work function. Note it down, then we will do a few more terms. This just single expression, you have to convert it in various Yes, written. Written up to equation number 5.
Sorry.
Yes, sir.
So now we will try to convert this work function into other forms. Like work function is again an energy. We can write this work function in terms of some wavelength, some frequencies. So the first concept comes of threshold frequency. The threshold frequency is the minimum frequency required for photoelectric emission. Or you can say that threshold frequency is the frequency corresponding to work function. So if you can write work function as h times some frequency, then that frequency is your threshold frequency. So instead of phi naught, you can write h nu naught, but remember, nu naught is a threshold frequency. Just like work function, this is fixed for a particular metal. Like if you take iron, the work function of iron is fixed. Similarly, the threshold frequency of iron is fixed. Threshold frequency is not the frequency of incident radiation. It's the minimum frequency at which the emission occurs. So this is corresponding to work function. So instead of phi naught, you can write h nu naught. So kinetic energy will be h nu minus h nu naught. Remember, threshold frequency depends on metal only. Depends on metal only. This depends only on metal, what metal you are using. Similarly, if you want, you can convert these frequencies into wavelength. Frequency is c by lambda. Nu naught is c by lambda naught. So this lambda is the wavelength of the incident radiation, and this lambda naught is the threshold wavelength. Threshold wavelength means wavelength corresponding to the threshold frequency. See, wavelength and frequencies are inversely proportional. So if threshold frequency is the minimum frequency, that means threshold wavelength is the maximum wavelength. So these are the relations that one should know to solve numericals on photoelectric effect. Do it. Note it down. Yes. I'm ending this class in 2 minutes. This is over. And the numericals we'll do in the next class. I'm just ending this class. Just 2 more minutes. Yes, everyone have written up to equation number 8.
Yes, sir.
Yes, sir.